Assalamualaikum warahmatullahi wabarakatuh. On this occasion, we will present about limit theorems. First of all, let me introduce our group. My name is Febriyanti Ervi M and my friends are Rembulan Permata O and Daffa Alim Sajid. In this section, we will obtain some results that enable us to evaluate the limits of certain sequences of real numbers. This result will expand our collection of convergent sequences rather extensively. We begin by establishing an important property of convergent sequences that will be needed in this and later section. The first definition, a sequence X, where X is defined as Xn of real numbers, is said to be bounded if there exists a real number m greater than 0, such that the absolute value of Xn less than or equal to m for all n element of natural number. Thus the sequence Xn is bounded if and only if the set Xn, which n is element of natural number, of its values is a bounded subset of R of real number. The second theorem is a convergent sequence of real numbers is bounded. The proof: suppose that limit of xn is equal to x and let epsilon is defined as 1, then there exists a natural number k is equals to k1 such that the absolute value of xn minus x less than 1 for all n greater than or equal to k. If we apply the triangle inequality with n is greater than or equal to k, we obtain the absolute of xn is the absolute of xn minus x plus x is less than or equal to the absolute value of xn minus x plus the absolute value of x less than 1 plus the absolute of x. If we set m is defined as the supremum of the set, the absolute value of x1, the absolute value of x2, blah blah blah, until the absolute value of x, k minus 1, and 1 plus the absolute value of x. Then it follows that the absolute value of xn is less than or equal to m for all n is element of natural number. The next is how the limit process interacts with the operations of addition, subtraction, multiplication, and division of sequences. If x is defined as xn and y is defined as yn are sequences of real number, then we define their sum to be the sequence of x plus y is defined as xn plus yn, their differences to be the sequence x minus y is defined as xn minus yn, and their product to be the sequence x product y is defined as xn yn. If we define the multiple of x by z to be the sequence cx is defined as c xn. Finally, if z is defined as zn is a sequence of real numbers with zn is not equals to 0 for all n element of natural number, then we define the quotient of x and z to be the sequence z is defined as xn divided by zn. For example, if x and y are the sequences, x is defined as 2, 4, 6, blah 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 until 2n blah blah blah, then y is defined as 1 per 1, 1 per 2, 1 per 3, blah blah blah, 1 per n until blah blah blah. Then we have for x plus y, we add x by y, we get 3, 9 per 2, 19 per 3 by adding 2 plus 1 per 1, 4 plus 1 per 2, 6 plus 1 per 3, and etc. For x minus y, we get 1, 1 per 1, 7 per 2, 17/3, and etc. And for x product y, 3 times x and x per y, we get the same with the step above. We note that if z is the sequence of z defined as 0, 2, 0, blah blah blah, 1 plus minus 1 power n, blah blah blah, we can define x plus y, x minus y, x product y, but x by z is not defined since some of the terms of z are 0. We now show that sequences obtained by applying these operations to convergent sequences give rise to new sequences whose limits can be predicted.
3.2.3 Theorem. A. Let x equal xn and y equals yn be sequence of real numbers that converge to x and y respectively, and let C in R. Then the sequence x plus y, x minus y, x dot y, and Cx converge to x plus y, x minus y, xy, and Cx respectively. B. If x equal xn converges to x and z equals zn is a sequence of non-zero real numbers that converge to z and z not equal to 0, then the Gaussian sequence x over z converges to x over z. Proof. A. To show that lim xn plus yn equals x plus y, we need to estimate the magnitude of absolute value xn plus yn minus x plus y. To do this, we use the triangle inequality 2.2.3 to obtain absolute value xn plus yn minus x plus y equals absolute value xn minus x plus yn minus y less than or equal absolute value xn minus x plus absolute value yn minus y. By hypothesis, if epsilon greater than 0, there exists a natural number k1 such that if n greater than or equal k1, then also there exists a natural number k2 such that if n greater than or equal k2, then hence if k epsilon equals sub k1 k2, it follows that if n greater than k epsilon, then absolute value xn plus yn minus x plus y less than or equal absolute value of xn minus x plus yn minus y less than a half epsilon plus a half epsilon equals epsilon. Since epsilon greater than 0 is arbitrary, we infer that x plus y equals xn plus yn converge to x plus y. Precisely, the same argument can be used to show that x minus y equals xn minus yn converges to x minus y. To show that x dot y equals xn yn converges to xy, we make the estimate absolute value xn yn minus xy equals absolute value xn yn minus xny plus xny minus xy less than or equal xn times xn minus y plus absolute value xn minus xy equals absolute value xn times absolute value yn minus y plus absolute value xn minus x times absolute value of y. According to Theorem 3.2.2, there exists a real number m1 greater than 0 such that absolute value xn less than or equal m for all n in n, and we set m sub m1 absolute value y. Hence we have absolute value x and y n minus xy less than or equal m absolute value y n minus y plus m times absolute value x n minus x. From the converged x and y, we conclude that if epsilon greater than 0 is given, then there exists a natural number k1 and k2 such that n greater than or equal to k1, then absolute value x n minus x less than epsilon over 2m, and if n greater than or equals to k2, then absolute value y n minus y less than epsilon 2 over 2m. Now let k epsilon equals sub k1 k2, then if n greater than or equals k epsilon, we infer that absolute value x n y n minus xy less than m times y n minus y plus m times absolute value x n minus x less than m times epsilon over 2m plus m times epsilon over 2m n equals to epsilon. Since epsilon greater than 0 is arbitrary, this proves that the sequence x dot y equals xn yn converts to xy. The fact that cx equals cxn converts to cx can be proved in the same way. It can also be deduced by taking y to be constant sequence c, 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 and so on. Next is for b. We next show that if z equals to zn is a sequence of non-zero number that converts to a non-zero limit z, then the sequence 1 over z of reciprocal converts to 1 over z. First, let alpha equals a half times absolute value of z, so that alpha greater than 0. Since lim zn equals z, there exists a natural number k1 such that if n greater than or equals k1, then zn absolute value zn minus z less than alpha. It follows from corollary 2.2.4a of the triangle inequality that a half absolute value of z equals absolute value z minus alpha less than or equal absolute value of zn for n greater than or equal k1. Therefore, 1 over absolute value z less than or equal to 2 over absolute value of z for n greater than k1. So we have the estimate absolute value 1 over zn minus 1 over z equals absolute value z minus zn over zn times z equals 1 over zn 1 over absolute value zn times z times absolute value z minus zn less than or equal 2 over z absolute value z square times absolute value of z minus zn for all n greater than or equals k1. Now, if epsilon greater than 0 is given, there exists a natural number k2 such that n greater than or equals k2, then absolute value z minus zn less than a half epsilon times absolute value z square. Therefore, it follows that if k epsilon sub k1 k2, then absolute value 1 over zn minus 1 over z less than epsilon for all n greater than k epsilon. Since epsilon greater than 0 is arbitrary, it follows that lim 1 over zn equals 1 over z. The proof of b is now complete by taking y to be the sequence 1 over zn and using the fact that x dot y equals xn over zn converts to x times 1 over z equals x over z. Some of the result of Theorem 3.2.3 can be extended by mathematical induction to a finite number of convergent sequence. For example, if A equals AN, B equals BN, until Z equals Zn are convergent sequence of real number, then their sum is a convergent sequence, and A plus B plus blah 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 plus Z equals AN plus BN plus blah 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 until Zn. 1. Lim AN plus BN plus blah 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 until Zn equals lim AN plus lim BN plus blah 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 plus C plus lim Zn. Also the product A dot B dot C dot blah 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 dot Z equals AN BN blah 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 Zn is a convergent sequence. 2. Lim AN BN blah 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 Zn equals lim AN times lim BN times blah 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 lim Zn. Hence, if K in N and if A equals AN is convergent sequence. 3. Lim AN power K equals lim AN power K.
3.2.4 Theorem. If x equals to xn is a convergent sequence of real numbers, and if xn greater than or equals to 0 for all n element of natural number, then x equals to limit xn greater than or equals to 0. The proof: suppose the conclusion is not true and that x less than to 0, then epsilon is minus x is positive. Since x converges to x, there is a natural number case such that x minus epsilon less than xn less than x plus epsilon for all n greater than or equals to k. In particular, we have xk less than x plus epsilon equals to x plus negative x equals to 0, but this contradicts the hypothesis that xn greater than or equals to 0 for all n elements of natural number. Therefore, this contradiction implies that x greater than or equals to 0. 3.2.5 Theorem. If x equals to xn and y equals to yn are convergent sequence of real numbers, and if xn less than or equals to yn for all n element of natural number, then limit xn less than or equals to limit yn. The proof: let zn equals to yn minus xn, so that z equals to zn equals to y minus x and zn greater than or equals to 0 for all n element of natural number. It follows from Theorems 3.2.3 and 3.2.4 that 0 less than or equals to limit z equals to limit yn minus limit xn, so that limit xn less than or equals to limit yn. 3.2.6 Theorem. If x equals to xn is a convergent sequence, and if a less than or equals to xn less than or equals to b for all n element of natural number, then a less than or equals to limit xn less than or equals to b. The proof: let y be the constant sequence. Theorem 3.2.5 implies that limit x less than or equals to limit y equals to b, and based on Theorem 3.2.5 implies that a less than or equals to limit x. 3.2.7 Squeeze Theorem. Suppose that x equals to xn, y equals to yn, and z equals to zn are sequence of real numbers such that xn less than or equals to yn less than or equals to zn for all n element of natural number, and that limit xn equals to limit zn, then y equals to yn is convergent and limit xn equals to limit yn equals to limit zn. The proof that w equals to limit xn equals to limit cn if epsilon greater than 0 is given, then it follows from the convergence of x and z to w that there exists a natural number k such that if n greater than or equals to k, then the absolute value of xn minus w less than epsilon, and the absolute value of cn minus w less than epsilon. Since the hypothesis implies that xn minus w less than or equals to yn minus w less than or equals to zn minus w for all n element of natural number, it follows that minus epsilon less than yn minus w less than epsilon for all n greater than or equals to k. Since epsilon greater than 0 is arbitrary, this implies that limit yn equals to w.
3.2.8 Example A. The sequence n is divergent. It follows from Theorem 3.2.2 that if the sequence x equals n is convergent, then there exists a real number m greater than 0 such that n equals absolute value n less than m for all n in n. But this violated the Archimedean property. B. The sequence minus 1 power n is divergent. The sequence x equal to minus 1 power n is bounded. Take m equals 1. So we cannot invoke Theorem 3.2.2. However, assume that a equals lim x exists. Let epsilon equals 1 so that there exists a natural number k1 such that minus 1 power n minus a for n greater than k1. If n is an odd natural number with n greater than or equals k1, this gives minus 1 power minus a less than 1, so that minus 2 less than a less than 0. On the other hand, if n is an even natural number with n greater than or equals k1, this inequality gives 1 minus absolute value 1 power minus alpha less than 1. Show that 0 less than a less than 2, since a can satisfy both of these inequalities, then the hypothesis x is convergent leads to a contradiction. Therefore, the sequence x is divergent. Next, C. Lim 2n plus 1 over n equals 2. If we let x equals 2 and y equals 1 over n, then 2n plus 1 over n equals x plus y. Hence, it follows from Theorem 3.2.3a that lim x plus y equals lim x plus lim y equals 2 plus 0 equals 2. D. Lim 2n plus 1 over n plus 5 equals 2. Since the sequence 2n plus 1 and n plus 5 are not convergent because it is not possible to use Theorem 3.2.3b directly, however, we write 2n plus 1 over n plus 5 equals 2 plus 1 over n over 1 plus 5 over n. We can obtain the given sequence as 1, to which theorem 3.2.3b applies when we take x equals 2 plus 1 over n and z equals to 1 plus 5 over n. Since lim x equals 2 and lim z equals 1 and not equals to 0, we deduce that lim 2n plus 1 over n plus 5 equals 2 over 1 equals 2.
The next example is limit of 2n per n squared plus 1 is equals to 0. Theorem 3.2.3b doesn't apply directly. We note that 2n per n squared plus 1 is equals to 2 per n plus 1 per n. But theorem 3.2.3b doesn't apply here either because n plus 1 per n is not a convergent sequence. And however, if we write 2n per n squared plus 1 equals to 2 per n plus 1 per n squared, we can apply theorem 3.2.3b. Since limit 2 per n equals 0 and since limit 1 plus 1 per n squared is equals to 1, which is not equal to 0, therefore limit 2n per n squared plus 1 is equals to 0 per 1 equals to 0. Next, limit of sin n per n equals to 0. We can apply theorem 3.2.3b directly since the sequence n is not convergent, neither is the sequence of sin n. It doesn't appear that a simple algebraic manipulation will enable us to reduce the sequence into 1, to which theorem 3.2.3 will apply. However, if we note that minus 1 per n less than or equals to sin n per n less than or equal to 1 per n for all n element n, hence we can apply this squeeze theorem 3.2.7 to infer that sin n less than or equals to 1 limit of sin n less than or equal to 1 limit of n power minus 1 sin n is equals to 0. We note that theorem 3.1.10 could also be applied to these sequences. Let x is defined as xn be a sequence of real numbers that converges to x element of real numbers. Let b be a polynomial. For example, let pt is defined as ak t power of k plus ak1 t power k minus 1 plus blah 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 plus a1t plus a0, where k element of natural number and ag element of real number for g is equals to 0, 1, blah 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 until k. It follows from theorem 3.2.3 that the sequence of pxn converges to px. Let x defined as xn be a sequence of real numbers that converges to x element real number. Let R be a rational function, that is Rt is defined as pt per qt, where p and q are polynomials. Suppose that qxn is not equal to 0 for all n of element of natural number, and that qx is not equals to 0, then the sequence of Rxn converges to Rx equals to Px per Qx.
3.2.10 theorem. Let x equals to xn be a sequence of real numbers that converges to x, and suppose that xn greater than or equals to 0, then the sequence square root of xn of positive square roots converges and limit square root of xn equals to square root of x. The proof: it follows from theorem 3.2.4 that x equals to limit xn greater than or equals to 0, So the assertion makes sense. We now consider the two cases. First, x equals to 0 and second, x greater than to 0. First case, if x equals to 0, let epsilon greater than to 0 be given. Since xn to 0, there exists a natural number k such that if n greater than or equals to k, the 0 less than or equals to xn equals to xn minus 0 less than epsilon square. Therefore, 0 less than or equals to square root of xn less than epsilon for n greater than or equals to k, since epsilon greater than 0 is arbitrary. This implies that square root of xn to 0. Second case, if x greater than to 0, then square root of x greater than to 0, and we note that square root of xn minus square root of x equals to square root of xn minus square root of x multiplied by square root of xn plus square root of x over square root of xn plus square root of x equals to xn minus x over square root of xn plus square root of x. Since square root of xn plus square root of x greater than or equals to square root of x greater than 0, it follows that absolute value of square root of xn minus square root of x less than or equals to 1 over square root of x multiplied by absolute value of xn minus x. The convergence of square root of xn to square root of x follows from the fact that xn to x. Theorem. Let xn be a sequence of positive real numbers such that L equals to limit xn plus 1 over xn exists. If L less than 1, then xn converges and limit xn equals to 0. The proof by Theorem 3.2.4, it follows that L greater than or equals to 0. Let R be a number such that L less than R less than 1, and let epsilon equals to R minus L greater than 0. There exists a number k element of natural number such that if n greater than or equals to k, then the absolute value of xn plus 1 over xn minus L less than epsilon. If n greater than or equals to k, then xn plus 1 over xn less than L plus epsilon equals to L plus R minus L equals to R. Therefore, if n greater than or equals to k, we obtain 0 less than xn plus 1 less than xnr less than xn minus 1 r squared less than blah 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 less than xk r power n minus k plus 1. If we set c equals to xk over r power k, we see that 0 less than xn plus 1 less than cr power n minus 1 for all n greater than or equals to k. Since 0 less than r less than 1, it follows from limit r power n equals to 0, and therefore from limit xn equals to 0. 3.2.11 Theorem. Let xn. There is a quote for you. Mathematics is a place where you can do things which you cannot do in the real world. Okay, thanks for your attention. Stay at home, stay healthy, and be happy. Sorry for our mistake. See you.